Hello. This is Nicholas, and I wanted to do a video deriving where the Jacobian comes from. So if you're not familiar with the Jacobian, but you are familiar with multiple integrals, the idea behind the Jacobian is basically an extension of single variable ideas of calculus of like U substitution and things like that. So for example, take the simple integral here, cosine of 2x dx. And you could probably do this integral in your head without actually doing the u sub, right? 1/2 sine 2x plus c. But one thing to kind of notice here is that we have cosine 2x, right? So if we were to graph this, and it'll become important to note later that we're actually graphing this on the xy plane, then, right, it goes something like that. Right? More or less. That's really not how it's kind of bad. But anyway, so if we were to perform the standard u sub here, right, if we were to let u equal 2x, then what would happen is we'd have just the standard graph of cosine of u, which would be a little more like elongated. So, right, something like that. It would have double the period length. So something like that, directed along the y-axis, and that's an important distinction to make. So what we've really done is we've transformed along the x-axis to the u-axis, and that's what we're doing here. And so notice that space in general has been increased by a factor of 2. In other words, like, say this is like 2 pi right here, and then say it's like 2 pi right here as well, then we're going to get from here to here double the area, right? So what we need to do is then multiply by a factor of 1/2 to account for how our space has changed with this simple transformation u equals 2x. And that's why when you integrate this, you have a 1/2 sine 2x. And so in general, the du that you get for here, which would be 2 dx, is like a correction factor for how space changes after you do this transformation, you could think of. And I'm using these kind of words because it generalizes very easily to higher dimensions. For example, let's consider a double integral. So a double integral means we are integrating over a 2D region to get a 3D volume, just like how in a single integral we're integrating over a 1D line to get a 2D area. So if we were to consider our region that we're integrating over, let's consider, I'm going to kind of work backwards here, but let's consider we have, where is it? Okay. This here, and we're on, say, the UV axis. So basically, like, we had to do a double U sub, if you will, because there's two different variables with respect to which we're integrating for, right? If we have a double integral over a region D of f of x, y, dA, then our dA is du dv. So we have integrating along the u-axis and then along the v-axis. And if f is continuous, we can do it the other way around as well by Fubini's theorem. So, and let's consider we start like with these, this is our region here in the UV plane. And it's basically like this nice rectangle, say. So we've got something like this. Okay, and so let's call this initial point here u0 comma v0, and let's call this point here u0 plus delta u comma v0. So that means that this whole length here is delta u. And let's call this point here u0 comma v0 plus delta v, and that makes this whole length here delta v. And so we apply this double u sub, if you will, like we've already applied it here, so we're on the UV axis already. But let's say we started out, right? So we're kind of working backwards here, but let's say we started out in the xy plane. So here we are in the xy plane. And how do we get from here? Well, we'll call our transformation t. And it's important to note that t has to be a one-to-one transformation. In other words, every unique point on every unique point uv has to map to one and only one unique point xy and vice versa. Otherwise, it wouldn't work. So let's say we're in this xy plane. We have this kind of wacky region that we're integrating over that might be harder as opposed to this rectangular region. And I don't know, let's say it's this kind of weird shape like this. Something like that. I just kind of pulled that out of thin air. Maybe like these two curves right here are the same, just shifted over some. And these two are the same, just shifted up and down some. Okay, so now let's consider how we could, like how space changes from this transformation here to this transformation here. How this whole region changes into this weird region here. So the idea is that we can let delta u and delta v go to 0, and we can get a good approximation of this region in the xy plane. And the way we can do that is by actually drawing a parallelogram here. And I'm going to draw lines tangent at this red point here, and they're going to be perpendicular to one another. So we have something like that. And I'm trying to draw it as nice as I can here for you. Something like that. And so I'm just kind of completing this parallelogram here. And so it's a parallelogram. Now, how did I actually define this parallelogram? So I define it as follows. Notice that this right here, this line is given by, if we've got like vector equations that make up this region here, say r of t, or well, r of u comma v. Normally they're parameterized in terms of t, but for here we'll just say r of u comma v. And so this line right here then, right here, is actually just r what it would be r sub u, right? The partial of r with respect to u times delta u. So that would be this vector right here, because the x-axis here is corresponding with the u-axis, and so if we were to work the other way, right, maybe apply our transformation in the opposite direction, t inverse, I guess, then that would, this line right here would correspond with the partial with respect to u, because that would give us a tangent line at that point going in the u direction there, tangent to that point. And so now we could say that this line correspondingly is just the partial of r with respect to v times delta v. And now notice that this parallelogram, right now at least, looks like a pretty bad approximation. But again, as delta u and delta v get closer and closer to 0, it becomes a better and better approximation for for how space changes as we apply our transformation. So, what would the area of this parallelogram be? Well, if we've got two vectors here that define it, then the area of that parallelogram is just the cross product of the two vectors, the magnitude of the cross product of the two vectors. So the area is given by the cross product of r sub u delta u, oops, I wrote a v there, r sub u delta u cross r sub v delta v. And the r sub u is partial with respect to u and partial with respect to v, which delta u and delta v are scalars, so we can write this as the cross product r sub u cross r sub v times delta u delta v. And now as interpreting it as a matrix determinant, we would have the matrix, the magnitude of the determinant of the matrix, I, J, K, and then our actual coordinates that we're starting with, we could call this, we could call it like x sub u, x sub v, right? The components of the partial with respect to u of the whole vector function r, if it's like if it's got components x sub u, x sub v, and then since we're in two dimensions, our z is like 0, and then likewise 0 here. And then for the r sub v, the partial with respect to v, we could call those components of our vector function r, call it x sub v, y sub v. And so it amounts to taking this determinant here. Now notice that the determinant, when we expand along the I, right, if we do I times this minor determinant, we are going to get 0. If we do J times this minor determinant, we're going to get 0. So really all it comes down to is the following. It's the magnitude of x sub u, y sub v minus x sub v, v, y sub u times the magnitude of k hat, d, or delta u, delta v, I'm getting ahead of myself. And the magnitude of k hat is 1. It's a basis vector in the z direction. So what we really get is x sub u, y sub v minus x sub v, y sub u, delta u, delta v. Delta u, delta v. Okay. Now again, as we let delta u and delta v go to 0, then they become respectively du, dv, and this part right here is what's so important enough that it has given a name to itself, or well, it's got a name from other people, and that's called the Jacobian, J, of this 2D transformation. And it's written normally as the absolute value, right, because it's this positive. We're taking the magnitude of the partial of x comma y over the partial of u comma v. And that's how you'll see it written. Basically, it means take all possible like permutations of x, y, u, and v. So, for example, what this would look like is we would have the matrix like this. We'd have the partial of x with respect to u, the partial of x with respect to v, the partial of y with respect to u, and the partial of y with respect to v. So that's like all possible permutations of those four that you can take. And that's what the Jacobian tells us, and it arises very naturally. I know I did this using just 2 dimensions, in other words, just like a double transformation, right, where we had a u equals something and a v equals something. But this could be readily generalized to n dimensions. If you were to do it in 3 dimensions, for example, you would, rather than, you would like start with a rectangular prism, and then you would approximate with a parallel pipehead. And then you would use the formula for the volume of a parallel pipehead, which if it's got like, you treat the sides as like vectors, then its volume is given by the magnitude of vector A cross vector B dot vector C. And you could use that formula, which I'm pretty sure I've derived in a previous video, to then see where the Jacobian in 3 dimensions comes about, if you will. And maybe I'll write it out just to help you all. If you've got it in 3 dimensions, that's the, you would see it written as the partial of x comma y comma z over the partial of u comma v comma w. And so you take all possible permutations of that. So what would that look like? We'd have partial of x with respect to u, partial of x with respect to v, partial of x with respect to w, partial of y with respect to u, partial of y with respect to v, partial of y with respect to w, partial of z with respect to u, partial of z with respect to v, partial of z with respect to w. And that would be the Jacobian for 3 dimensions using the variables u, v, and w. As kind of a treat, I guess, since we have this thing here, remember in double integrals, when you convert to polar coordinates, for example, if you have the iterated integral in Cartesian, say like from a to b, c to d, of f of x, y, dx, dy, and you go to polar, then that changes to the integral from theta sub 1 to theta sub 2, r sub 1, r sub 2, of, say, f of x becomes r cosine theta, y becomes r sine theta, but then dx dy becomes r dr d theta, r dr d theta. And so where does the r come from? Well, it comes from the Jacobian, right? So if we consider the transformation x equals r cosine theta and y equals r sine theta, then the derivation of this is super simple, right? All right, we have partial x with respect to r, partial x with respect to theta, partial y with respect to r, and partial y with respect to theta, which is partial x with respect to r, that's cosine theta, partial x with respect to theta is negative r sine theta, partial y with respect to r is sine theta, partial y with respect to theta is r cosine theta, which is r cosine squared theta minus negative r sine squared theta, so plus r sine squared theta, and cosine squared theta plus sine squared theta is 1. That just gives us an r. And that's where the extra factor of r comes from in the double integral transformation to polar coordinates. I hope that... also one other thing I'd like to mention from a linear algebra standpoint, that the Jacobian also makes sense, because if you know anything about determinants at all, what they visually represent, they represent the magnitude by which some generic area in space changes. If you're to think of a matrix as like a vector transformation on space. So as an example, like if you start with any generic region, again, let's consider in say 2 dimensions here. If we start with like the basis vectors I hat and j hat, and we consider like the unit square that they form, and then let's say we have like this matrix, which is actually really just a vector transformation. Let's say, 2, 0, 0, 3. That matrix. We know that the determinant of that matrix is 6. And so what does that 6 actually represent? It represents the area, or the scalar by which any region in space is multiplied by, so that its area after the transformation remains the same as it did like before. So if we were to draw this transformation, what would it look like? Well, what this visually tells us is that this first part here of the matrix is like our x vector, and the second part here is like our y vector. So our x vector, which in this case is the unit vector I hat, goes to 2, 0, right? And then the y vector, which in this case is the unit vector j hat, goes to 0, 3, which is up here. And if we were to consider that same or corresponding region in space formed by those 2 vectors, you would see that it just forms a 2 by 3 rectangle, which of course has an area of 6, and that's what the determinant of 6 corresponds to. It's an area, because any matrix, any square matrix, can be viewed as a vector linear transformation on the space. So the Jacobian is nothing special about that at all. The Jacobian is a square matrix, and therefore is, when we take the determinant, telling us the scalar by which any generic region in space changes after the transformation. And we keep this positive, in other words, take the absolute value of the Jacobian, because the area or volume or whatever is a positive quantity. So there's two different perspectives on what a Jacobian means. I hope you can see that it's a intuitive construct. We didn't just pull it out of thin air from the math gods. I think